Good morning, I am Devasena. In this lecture, we are going to discuss about the topic polar plot. This polar plot topic is present in the subject control system. Polar plot theory. The polar plot of a sinusoidal transfer function g of j omega is a plot of the magnitude of g of j omega versus the phase angle of g of j omega on polar coordinates as frequency omega is varied from 0 to infinity. Thus, the polar plot is the locus of magnitude of g of j omega, angle of g of j omega as the frequency omega is varied from 0 to infinity. The polar plot is usually plotted on the graph sheet. The polar plot has concentric circles and radial lines. The circles represent the magnitude and radial lines represent the phase angles. Each point on the polar graph has a magnitude and phase angle. The magnitude of a point is given by the radial line passing through that point, and the phase angle is given by the radial line passing through that point. In a polar graph sheet, a positive phase angle is measured in anticlockwise from the reference axis 0 degree, and negative phase angle is measured clockwise from the reference axis 0 degree. In order to plot the polar plot, magnitude and phase angle of g of j omega are computed for various values of frequency omega and tabulated. Usually, the choice of frequencies are corner frequencies and frequencies around corner frequencies. Choose proper scale for the magnitude circles. Fix all the points on the polar graph sheet and join the points by smooth curve. Write the frequency corresponding to each point of the plot. A representation of the polar graph sheet is shown below. The polar graph sheet comprises of concentric circles and radial lines. The concentric circles represent the magnitude value of the polar plot, and radial lines represents the phase angle of the polar plot. Alternate way of expressing g of j omega in rectangular coordinates. Alternatively, if g of j omega can be expressed in rectangular coordinates as g of j omega is equal to g suffix r of j omega plus j into g suffix I of j omega, where g suffix r of j omega is equal to the real part of the g of j omega and g suffix I of j omega is equal to the imaginary part of g of j omega. The polar plot can be plotted in ordinary graph sheet between g suffix r of j omega, that is the real part of j omega, g of j omega, and g suffix I of j omega, that is the imaginary part of g of j omega, by varying frequency from 0 to infinity. In order to plot the polar plot on ordinary graph sheet, the magnitude and phase angle of g of j omega are computed for various values of frequency omega. Then convert the polar coordinates to rectangular coordinates using polar to rectangular conversion in the calculator. Sketch the polar plot using rectangular coordinates. The starting and end points representation of the polar plot. For minimum phase transfer function with only poles, type number of the system determines the quadrant at which the polar plot starts, and the order of the system determines the quadrant at which the polar plot ends. The minimum phase systems are systems with all poles and zeros on left half of the S-plane. Determination of the change in shape of the polar plot. The change in shape of the polar plot can be predicted due to the addition of a pole or zero. When a pole is added to a system, the polar plot endpoint will shift by minus 90 degree. When a zero is added to a system, the polar plot endpoint will shift by plus 90 degree. Starting points of type 0, type 1, type 2, type 3 systems. As we already stated that the starting point of the polar plot is determined with the help of type number of the system. Here is a representation of the starting points of type 0, type 1, type 2, type 3 systems. The starting point of type 0 system is from angle omega is equal to 0 degree. The starting point of the type 1 system starts from minus 90 degree. The starting point of the type 2 system starts from angle minus 180 degree. Similarly, the starting point of the type 3 system starts from minus 270 degree. Endpoints of polar plots of all poles minimum system. We know that the endpoint of the polar plot is determined with the help of the order of a system. Here is a representation. The endpoint of the first order system is at minus 90 degree. Similarly, the endpoint of the second order system is at minus 180 degree. The endpoint of the third order system is at minus 270 degree, and the endpoint of the fourth order system is at minus 360 degree. Polar plot of type 0 order 1 system. As we already indicates that the starting point of the polar plot is determined with the help of the type number of the system, and the endpoint of the polar plot is determined with the help of order of the system. Here is the representation of type 0 order 1 system. The starting point of the type 0 order 1 system starts at phase angle 0 degree, and the endpoint of the type 0 order 1 system is at minus 90 degree. The representation is here. Polar plot of type 0 order 2 system is shown below. As we already know that the type 0 system starts from the phase angle 0 degree. The order 2 system ends at minus 180 degree. This is represented in this diagram. In this polar plot, the representation of type 0 order 2 system is represented. That is, the starting point of the polar plot is 0 degree for type 0 system, and the end point of the polar plot is minus 180 degree. That is, the starting point of the polar plot is determined by the type 0 system, and end point of the polar plot is determined by order of the system. This is represented in the diagram. Polar plot of type 0 order 3 system is shown below. As we already know that the type of the system indicates the starting point of the polar plot, and order of the system indicates the end point of the polar plot. In this diagram, we have type 0 order 3 system. That is, the starting point of this polar plot is from 0 degree phase angle, and end point of this polar plot is minus 270 degree. This is represented in this diagram. Now we are going to see the polar plot of type 1 order 1 system. The diagrammatic representation of type 1 order 1 system is shown below. In this graph, we have type 1 order 1 system representation. This is indicated here. Now we are going to see the polar plot of type 1 order 2 system. The diagrammatic representation of type 1 order 2 system is here. Now we are going to see the polar plot of type 1 order 3 system. The diagrammatic representation of type 1 order 3 system is shown below. In this diagram, the type 1 order 3 system is having the starting point from minus 90 degree and the end point at minus 270 degree. We are going to discuss about the procedure for drawing the polar plot. Step 1. Only open loop transfer function of a system must be considered. Step 2. If the system has unity feedback, then consider G of s value only, because the value of H of s is equal to 1 for unity feedback. Step 3. If the block diagram is given, then multiply the forward block gain with feedback path gain to get open loop transfer function. Step 4. Substitute S is equal to J omega, where J value is equal to square root of minus 1 and omega is the frequency which is represented in radians per second in the given open loop transfer function. Then step 5. Write the magnitude and phase equation for the given equation with the help of standard functions which we have already discussed above. Step 6. Calculate the value of magnitude m and phase angle phi for different frequencies. In general, we have to select the value of frequency omega as 0, 0.2, 0.4, 0.6, 0.8, 1.0 and it goes on as 10, 100, thousands. Step 7. Draw the polar plot. It is usually drawn on the polar graph sheet. It has concentric circles and radial lines which indicate the phase angle of the polar plot. The positive angles are measured in anticlockwise direction and negative angles are measured in clockwise direction. Step 8. Gain crossover. Gain crossover is the point where the polar plot touches the unity circle. The angle measured at this point is named as gain crossover angle, which is represented as phi suffix GCO. Phase crossover. Phase crossover is the point where the polar plot touches minus 180 degree line. The magnitude measured at this point is phase crossover magnitude, which is represented as magnitude of G of J omega suffix PCO. Now we are going to determine gain margin as well as the phase margin. First we will discuss gain margin. Gain margin is represented by a letter K suffix G. It is defined as the reciprocal of the magnitude of open loop transfer function evaluated at the frequency omega suffix PCO. It is represented as K suffix G is equal to 1 divided by magnitude of G of J omega suffix PCO. Then phase margin nu. It is defined as the additional phase angle lag at gain crossover required to bring the system to limit the system instability. It is represented as nu is equal to 180 degree plus phi GCO. Representation of gain crossover and phase crossover in the polar plot. Here we have a polar plot. First we have to draw a unity circle. Then we have to draw the polar plot. The gain crossover frequency is the frequency where the polar plot intersects the unity circle. This is indicated in this diagram. Similarly, the polar plot intersects the minus 180 degree at one frequency. That frequency, the corresponding frequency is represented as phase crossover frequency. Now we are going to analyze the system stability in polar plot. The representation of the polar plot for stable system and unstable system is given here. We have already calculated the gain margin as well as the phase margin. With the help of this gain margin and phase margin, the system stability can be analyzed. If we have positive gain margin and positive phase margin, then the system is said to be a stable system. If the calculated gain margin and phase margin is negative, then the system is said to be unstable system. This is indicated in this graph.